Welcome to a brief explanation of the principles governing normal phase chromatography, and on a little bit more practical note, how we can use thin layer chromatography to identify and separate compounds from mixtures. Let's begin our discussion with a question. And that question is, how does partitioning between the stationary and mobile phases help us to separate compounds from a mixture by thin layer chromatography? In order to answer this question, we'll need to introduce a cast of characters first. Let's start by defining silica as gray spheres. This will be the stationary phase in our example. Next, let's use blue spheres to represent solvent molecules. These will be representing the mobile phase. We'll have a low polarity compound represented by yellow polygons, and a compound of higher polarity, which will be represented by purple polygons. Now let's use these simple objects to set up a demonstration where we can watch what happens when we introduce these two compounds into a simple chromatographic system. Let's begin as we usually do, by zooming in to the apparatus that we'll be using at the molecular level. So let's take a look at this chromatography plate, but much, much closer. When we zoom in this close, what we expect to see is an array of stationary silica over which is flowing mobile phase. So in this case, the surface of the plate would be represented by the stationary gray spheres, while the wicking mobile phase moving upward across the plate would be represented by the moving blue spheres. If we introduce one of our analyte molecules at the upstream end of this chromatographic system, we can expect it to move and be carried along by the mobile phase anytime that it is not adhered to the stationary phase. But recall that this purple compound is one of relatively high polarity. This means that its affinity for the stationary phase in normal phase chromatography will be very high. So let's release this into the chromatographic system and see how this high affinity for the stationary phase affects its mobility. You'll notice that as the compound is swept into the mobile phase, it moves along the system, but that every so often it adheres to the silica stationary phase and has a relatively long residence time there. The consequence of this is that this molecule moves very slowly across the silica plate. If instead we introduce our low polarity compound to the system and then release it, we'll see a slightly different behavior. Recall that lower polarity compounds will have weaker interactions with the stationary phase. Because of this, when we release the compound, it's carried along at the same rate by the mobile phase, but it spends a greater percentage of its lifetime in there, which means that it's going to move overall faster than the previous compound did. The utility of this observation is best seen when we release a mixture of both compounds into the system. When we do this, notice that the yellow compound travels at an overall faster rate because its residence time on the stationary phase is less. And the practical consequence of this is that these two compounds are separated in space from one another. And this is ultimately the utility of chromatography. Now, instead of zooming all the way down to the molecular level, let's take a look at our TLC plate as though the entire screen were a single plate. In doing this, we can visualize how a TLC experiment will work as we go through the setup, the development, and the analysis of the plate. The first step in any TLC analysis is to define the starting lane by making a line with a pencil. The starting lane should be positioned in such a location that it will not be dipped into the solvent when placed in the developing chamber, but which leaves a large amount of the plate above that starting lane for the chromatography to take place. At this point, we'll spot first a spot of the purple compound, then a spot of our yellow compound, and also a mixture, labeling each of these lanes so that they're easily identified once the experiment is complete. Once we have applied our samples to the plate, the next step is to develop it by placing it inside the chamber and allowing the mobile phase to move upward through the plate by capillary action. So here comes our flowing mobile phase. As it reaches the compounds, it will begin to transport them at a rate which is a function of their polarity. Notice that the yellow compound is traveling faster than the purple compound. And notice also that the spot, which was originally a mixture, now has all of its components separated along the plate. Now we can qualitatively at this point say that the yellow compound must be less polar than the purple compound because it moved faster within this chromatographic system, which we know is normal phase. However, it's usually more of interest to us to quantify this kind of behavior. As scientists, we'd like to have numbers to associate with these mobilities. In the case of thin layer chromatography, we use something called the retention factor. To calculate this, we measure the distance traveled by the solvent from the starting lane to the end of the solvent front. We then also measure the distance traveled by each sample from the starting lane to the center of the spot where it remains at the end of the experiment. We can then calculate the retention factor by dividing the distance traveled by the sample with the distance traveled by the solvent. Therefore, in our case here, the yellow compound would have a higher RF value because it traveled a greater distance and therefore must be less polar.